morning, everybody. I just wanted to recapitulate what we did last time. I wasn't very satisfied about the presentation of the finite square well. So let me just, first of all, it's probably better to just set the zero of the potential here and have the wells here at height V0. This is easier if you want to do the limit V0 going to infinity. Then it becomes exactly the infinite square well. With the setup of last time, we had zero energy here and minus V0. There was a shift of energy, okay? Now, for the bound states, the extended states, you have to do it yourself. It's the exercise. For the bound state, we discussed that you can distinguish even and odd states because of the parity of the potential. And inside, I call the wave function cos kx or sine kx if even or odd with some coefficient b. Outside, it must be evanescent wave, so a e to the minus qx, and here plus or minus the same, okay, depending if even or odd. K is related to the energy directly, so K is just, energy is just h bar k squared over 2m. I remind you, we have to find the energy, or if you want to find the K, okay, because this is a discrete state that we have to find. And Q is also related to the energy, which I still have to find in this way, okay? Now, the two equations for the even state and the odd states are very, very simple. In one case, I have tangent of Ka equal to Q over K. In the other case, the same quantity, Q over K, is equal to minus the cotangent, okay, of Kx. Now, here I draw the tangent in green. Okay, so this is the tangent of Ka, the green ones, and this is Ka. And in yellow here, is it yellow? It is kind of yellow. Okay, I draw the minus the cotangent of Ka here. Okay, there are the standard places where you have zeros and divergences. Okay, they are basically shifted one to the other. The drawing is not very nice, I recognize, okay? But you have to think of this to be shifted here for the cotangent, for minus the cotangent. Again, the other branch of the tangent, again, a shift becomes minus the cotangent and so on, okay? All right. Now, to solve the equation, you have to equate everything to Q over K. And here, last time I wasn't particularly effective in presenting the thing. It's very, very simple. That's the pity of it. So this is V0 minus E, but E is just h bar square K square over 2m, okay? So K over Q, or Q over K better, okay, which is the quantity that appears on the right-hand side, is very simple. You can just show it's equal to 2m over h bar k square V0 minus 1, okay? It's very simple from here. You divide by h bar k square over 2m, and then you take the square root, and you get this directly. This can be written in many ways, okay? One way of writing it is, for instance, to notice that this is the energy. So this can be written also as square root of V0 over the energy minus 1, or if you want V0 minus the energy over the energy. Obviously, the energy has to be less than V0, okay? Or another way of writing is totally equivalent, is, for instance, to write it like this. Square root of 2m a square over h bar square times V0 divided by Ka square minus 1. Okay? Now this object here, you see, has the dimension of what? Nothing. It's a number. It's a ratio of V0 divided by the confinement kinetic energy, h bar square over 2m a square. Okay? So this is a dimensionless value for the height of the potential. Ka is, in fact, also a number, which is my scale here. Okay? So in either way you draw it, you notice that when k becomes very small, okay, this quantity just diverges, so it goes always here. However, the final destiny, okay, so when, for instance, the energy approaches V0, or k approaches the appropriate quantity such that this is 0, it's just a square root type of singularity, and really depends on V0. The larger is V0, the more this thing, okay, goes on until it dies off, okay? So if V0 is very small, you can verify that this object essentially drops very soon here, okay? So this is V0 small. Obviously small in units of h bar square over 2ma square, okay? And you have only one bound state, the even lowest state, this one, okay? If you keep increasing V0, progressively you do something like this, zack. Here you have one even and one odd state. And then you increase further again, and you have one even, one odd, and one even again. And you increase this even further, okay? Well, it's very ugly drawing, but even, odd, okay? So depending on your value of V0, you can draw these things, for instance, on the computer and decide how many. Well, in fact, to decide how many, it's even simpler. You don't have to find them. You can just verify where this point ends up, okay? And you know that if it is, for instance, between pi over 2 and pi, then you must have this situation, right? And this point is simply where Ka is exactly equal to that quantity. So that the result is just 0, okay? So it's very simple to count how many you have. It's more complicated to find them because you have to solve this non-algebraic equation, okay? Either one of the two. It's trigonometric. It's a bit non-trivial to do it, but it can be done, for instance, with some numerical algorithm, okay? For V0 very, very large, this thing becomes essentially up in the skies, and the solutions are all up here in the skies, okay? And you verify again that they are exactly for k equal to the ones that you obtain for the infinite square well, okay? Is this more, reasonable? Okay. This type of graphical solution are often useful, okay? There are variations of this problem. For instance, you might think of doing asymmetric wells, or you might do two square wells, one after the other, okay? The problem becomes increasingly more complicated, but usually with graphical techniques you understand better things, okay? So if there are no specific questions, I would move on. And move on to a problem that I know you have done already. It's the harmonic oscillator problem. But I want to go through it, at least in some quick way, because it's... Can I erase? No. This? No. Okay. I will start from the right. Now, this problem occurs so often, okay, in many problems in physics that it is one of the prototypical things that you must be really ready to do without much effort, okay? For instance, if you study the vibrations of a molecule, you have two atoms, the potential that keeps the two atoms together, it's not harmonic, okay? It's something like this, okay? So if this is the distance between the two molecules, okay? For instance, two hydrogen in a hydrogen molecule, okay? So there is some equilibrium distance, okay? However, the two atoms are fluctuating objects. Don't think that they sit exactly there, either because of temperature or even in absolutely zero temperature because of quantum effects. They just fluctuate over this thing. But you can think, okay, under as a rough approximation, at least, that this is just a quadratic object, okay? So you can calculate some of the properties of this vibrating object with an harmonic potential, okay? And in many other cases, close to minima, it's a reasonable approximation, okay? Certainly because it is one thing that you know how to do and maybe the only thing that you know how to do in the problem, okay? Good. Okay, so this as a general justification. Can I proceed with the, okay. Now, the setting up of the problem, I encourage you to go dimensionless soon, okay? The problem is, in general, as follows. You have some Hamiltonian, okay, that is momentum square over twice the mass plus 1/2 m omega square coordinate square, okay? Now, I'm drawing them, first of all, capital, for a reason that we will understand soon, and in general, three-dimensional vectors, okay? So this would be the three-dimensional harmonic oscillator. Now, as you notice, this is just px squared plus py squared plus pz squared over twice the mass. And also this is a sum of, for instance, x squared plus y squared plus z squared, okay? Therefore, the full Hamiltonian is really not intrinsically three-dimensional. It's just a sum of an Hamiltonian that regards x, for instance, which appears there, an Hamiltonian that regards y, which appears there, and an Hamiltonian that regards z. Okay? So the three coordinates really appear as sum of terms. And another important property is that these three coordinates really don't talk to each other in the quantum mechanical sense, in the sense that, for instance, px does not commute with x, but certainly commutes with y and with z, okay? So the non-trivial commutators are only x with px, okay? For instance, this is IH bar, but, for instance, x and py or pz would be just 0, okay? All in all, anything appearing here commutes with anything appearing here and there, okay? So they are so-called separable Hamiltonians, okay? We will encounter another important example of separation of variables in the Hamiltonian, and this is the example of hydrogen atom, okay? Or in general of a central potential. In that case, we will be able to separate the angular part of the motion from the radial part of the motion by working in spherical coordinates, okay? We'll do that next. Here, it's a separation of variables in Cartesian coordinates, which happens to be there in some problems, okay? Not many, but in some. Okay, whenever you have a separation of variables in the Hamiltonian, you can actually reduce the complexity of your problem, and this is pretty general, not so much for the harmonic oscillator. Even if here you have Vx plus Vy and Vz, it would still apply, okay? And you can solve the problem in this way, okay? Let me just quickly mention the problem. So suppose that you know how to solve each one of those things separately. I will call H alpha. Alpha could be x, y, and z. Solving means what? Means knowing the wave functions, okay? So psi n, let me label them by alpha because to remind us that this is, for instance, the x or the y or the z thing, okay? So this would be wave functions, and these are the corresponding energies, okay? So suppose you know how to solve this for x, y, and z separately. Obviously, they are essentially the same problem. Although I might even allow myself some freedom in omega. Rather than being a sphere, this might be an ellipsoid. So, for instance, omega x square might be different from omega y square and omega z square, okay? You have more freedom than what I was really doing before. But nevertheless, I can essentially solve the three in identical ways, apart from a change of parameter, possibly. Okay, I know how to do this. How can I write a wave function now, psi, for the full problem, so x, y, and z? That is my question, okay? And the thing I want to prove is the following, that you can essentially write this as a product of the three separate problems. So psi x, index, say, n, times psi y, index, let's call it m to distinguish it, okay? Times psi z, index L, okay? So in general, three possibly different wave functions with indices n, m, and L from the separate problems, okay? Collected together, glued together with a product, okay? Obviously, on the left-hand side, the wave function will depend on the collection of indices n, m, and L, okay? Now, let's prove that this is a wave function of the full H. Very, very simple thing. And in fact, we will see that the corresponding energy, which also has labels A, N, M, L, is this time not the product, but the sum. So it's E x n plus E y m plus E z l. Okay? The proof is very, very simple, but let me sketch it. So you have the Hamiltonian, that is the sum, okay, acting on the wave function, that is the product. Let me be sketchy, not to indicate the x and y and z, because you know what they are. Okay? So let's apply the Hamiltonian. First term acts only on this, okay? And when acting, it produces what? It produces exn times the same function, psi x n, psi m y, psi l z. Okay? The second piece acts on this. Notice, in order to act on the second piece, it has to jump over the first piece of the wave function. But it can do so because the y momenta and coordinate commute with the x, okay? So you can actually just move this operator just there. And when it gets there, it produces for me just another plus E, Y, M, okay? The third contribution, also in the same spirit, jumps over these two because they commute, acts on that and produces EZL. Okay? That's it. You have proved that the product wave function is indeed a wave function for the problem with eigenvalue equal to the sum of the three individual objects. Okay? So it's enough to solve this problem in any dimension to just solve a one-dimensional problem at the time. All right? Questions? Okay. So let us now concentrate, therefore, on the corresponding one-dimensional version. Which is, yeah.
Could you explain a bit about the potential profile that you drew at first?
Which one?
The first potential
Oh,
profile.
yes. Okay. Yeah. I was alluding to this. You have two atoms, for instance. Just make me definite. This is a hydrogen atom, and this is another hydrogen atom. Okay. So here there is a nucleus, and here there is an electron. Here there is a nucleus and one electron. You can ask yourself, these are two atoms. If they are far away, they feel each other very little, okay? But they feel each other, by the way, okay? Even if they are neutral objects, okay? Then you know that they have a van der Waals attraction, okay? Now, so you can ask yourself, given the separation R between the two nuclei? What is the interaction between these two entities? Okay. Well, if R is very, very large, you know that they attract each other with a van der Waals tail. Okay. So this is something like minus C over R to the 6th. We will do this, by the way, explicitly when we will do perturbation theory. Okay. So this is one standard exercise to just get this tail. When the distance becomes closer and closer, this attraction sooner or later has to give way to an actual repulsion, because when the electrons get close together and the two nuclei also get close together, they don't like each other very much. Okay? It is approximately of the angstrom scale. Okay, the equilibrium distance of the hydrogen atom is, I forgot how many angstroms, but is on the angstrom scale. Okay, two. What?
The size of an atom is like 10 raised to minus 10, like 1 angstrom.
It's like 10 to the 2 times 10 to the minus 10 meters. Okay, 2 angstroms roughly. Okay. So this is 2 angstroms. So strong repulsion there, and obviously this has to connect with an attraction at large distances. And in the middle, there is an equilibrium distance. Okay, there are many forms that look like this that are usually empirically used. By the way, to get it from actual quantum mechanical calculation, it's not a trivial thing, okay? Because it's a many-body problem. We have 2 protons, 2 electrons, but many-body. A few body problems, but accurate calculations are not trivial. Sometimes people approximate this with the so-called Lennard-Jones potential, which has a 1 over R to the 12 repulsion here, and minus 1 over R to the 6 attraction at large distances. But there are the other forms. And in any case, if I ask you, for instance, two water molecules, okay, what is the potential between the 2 water molecules? Well, it's a complicated thing. First of all, they are no longer spherical objects, okay? They have angles, okay? So you have to account also for angular dependencies. The 2 hydrogens, when facing each other, what is the potential? It's a complicated calculation. But people need those things to, for instance, perform molecular dynamics simulations. Okay, you want to integrate Newton's equation to simulate liquid water, for instance. Okay, just to then you have to know the potential, and the potential is an ingredient that has to be obtained in principle from a quantum mechanical calculation, not completely trivial.
One question.
Yeah.
There, I mean, I think we have to put something. Okay, the distance cannot be 0, right?
It's not 0, in fact. Yeah. I mean, this diverges. But the scale over, I mean, once again, there are. You shouldn't be too worried about those things in condensed matter. Okay, I never let the 2 nuclei to come in contact, essentially, because this is a tremendous energy, okay? You have to overcome a huge Coulomb repulsion, first of all, and then, obviously, nuclear forces will come into play. So you can access those things only if you take the 2 protons and you hit one against the other at very high energies, okay? Then you can ask yourself, what will the 2 protons do? But this is not, I mean, with the energies you access in molecules, you never really look at this part of the thing. This is the reason why you can essentially put almost whatever you want here, okay? The 2 things will never touch, far away.
This is a good approximation if we consider 2 molecules or something.
Right, right. Yes, in this region here, okay? Not really there. Okay. So let me go back to this problem. Now written in a 1D version, okay? So I now eliminate the vector, and this is now really x. But I keep drawing, if you notice them, just a capital letter. It is a typographical convenience because in a second I will have to introduce small x and small p because I want to teach you how to make things dimensionless. I mean, after all, you see, there is a mass in this problem. This mass could be the mass of an electron or the mass of whatever light particles you have there. Okay, there is an h bar in the problem because x and p do not commute. There is an omega in the problem, okay? So several units, okay, several quantities that might have numbers like 10 to the minus 31 kilograms, okay, or 10 to the minus 34 for h bar. Okay, you don't really want to put those numbers in your piece of paper, okay? You want to somehow get rid of them. And you will see that the solution, once you get rid of those things, it looks simpler to write. Second, how do you really do this? By just putting m equal to 1 in your formulas, omega equal to 1, and h bar equal to 1. This is something that you often find in the books. They say, okay, let's put the mass equal to 1, h bar equal to 1, and omega equal to 1. And everything then looks like this, p squared over 2 plus 1/2 q squared, okay? Or x squared. And then they continue. This is certainly a possibility, extremely drastic, and it's justified by some reasoning, and I want to teach you the reasoning behind, okay? The reasoning is to make explicitly clear which are the new lengths, times, and what are the units? Meters for, I mean, so lengths, masses, and time, right? Seconds or whatever. You can choose other units rather than the meter, the kilogram, and the seconds, okay? And measure everything in your units, okay? Appropriate units. In those units, things can become much simpler than just using the standard units, okay? Let me show this to you. First of all, okay. If I have a certain length in this problem, so this spring is elongated a certain length L, you can certainly write that the potential energy is this, right? So this is an energy associated with distance L stretching of whatever spring you have in this problem. Okay, on the other hand, this object here, remember, this is really minus h bar square over 2m, the second derivative with respect to x, okay? I'm writing it explicitly. So here, I also have energies, and this time, the characteristic energy, if I have a certain length L, will be h bar square over twice the mass, length square. You see derivatives, okay? So this would be like the confinement energy, kinetic energy for a particle in a certain length L. They're both energies, okay? Let me look for a length, okay, a specific L that satisfies this equation, okay? It's not particularly important why I select. I mean, I might select here with different factors. It doesn't really matter. It's just a possible choice of L, okay? So my unit of length will be L that satisfies this equation here, okay? Let's see what are the consequences. So, for instance, let's solve it. The 2 goes, and I have that L square is equal to h bar square divided by, no, sorry, L to the 4th, because L goes there, is equal to h bar square divided by m square omega square, okay? or if you want, L square equal to h bar over m omega. Okay? So there is a length which is related to h bar, to the mass, and to omega, which is apparently useful in this problem. Okay? Now, these are 10 to the minus 34, 10 to the minus, I mean, whatever. No matter what they are, this length seems to be relevant, and we will use it now. For instance, rather than measuring things with the standard units, okay, let us use x, small x, equal to big X divided by this length. Okay? This is now dimensionless. Okay? In other words, it measures x in units of this such and such, whatever, meters. Okay? It doesn't matter how many meters. It's L. There. What about P? P also has dimensions, obviously. And if I select L to be my units of length, the units of momentum would be h bar over L. Okay? Because remember that is minus I h bar, the gradient. So the unit here should be h bar over L. Okay? So I define two new coordinate and momenta, okay, which are x over L and p over h bar over L, or if you want, p times L over h bar. Okay? Both are dimensionless. And first of all, let's calculate the commutator. Okay? You remember that the commutator of x and p was I h bar. Now, what about that of x and p, small x and small p? Well, x, p, just substitute for x L times big X, and substitute for P L, sorry. Huh? Sorry, this is over L, and this is L P over H bar, okay? Now, these are just constant, and you see that in both terms of the commutator, the L drops. So this is equal just to 1 over h bar, the commutator of big X and big P, which is I over h bar, I h bar. So the h bar drops, okay? The result is just I, okay? So it's like if h bar now has been set to 1. But I never set it to 1. I mean, I just used new units of length. All right? Let us see what happens to the Hamiltonian with this choice of units. For instance, p squared over twice the mass is equal to, well, p is just h bar over L small p, okay? So it's h bar square over L square small p square plus 1/2 m omega square. Big X is equal to L times X, so this is L square omega square, okay? Now, perhaps you notice immediately that here I have a quantity that is exactly the thing that guided me in finding L, okay? So these quantities are exactly the same by choice. So let me put just in front of both of them. And by the way, what are they? Okay, so let's just put the factor 2 back again. So if L is this, for instance, how much is 1/2 m omega square L square with this choice? Well, it is h bar over m omega. You see? So this goes, h bar omega divided by 2. Okay? Good. So both these things are h bar omega divided by 2. The first is then p square, and the second is just x square. Okay? So if I measure now my energies okay? Let's call it H tilde to be the Hamiltonian divided by H bar omega. The energies are now measured in units of H bar omega, the natural unit, okay? This is now a dimensionless Hamiltonian. You see, no dimension. And how much it is? It is just 1/2 p squared plus x squared. The miracle has happened, okay? Everything looks like is one. Mass, omega, and length, okay? Now, if I ask you, after finishing solving this problem, okay, tell me, for instance, how many joules is this energy? Or tell me how much is this length? You can actually, from the formulas, reconstruct exactly the actual units you need to use, because you know how to transform the variables in the old ones, okay? Energies, lengths, and whatever, okay? So you can actually reconstruct at the end of every calculation the exact numbers that you would need, for instance, to tell to some experimentalist. You cannot tell the guy the energy is 1.3, but 1.3 what, okay? You have to give him indication of the units you have used. And if you simply drop everything and you don't never keep track of the units, the information is a bit lacking, okay? So you always have to make sure that you have done your variables dimensionalization in such a way that you can actually reconstruct, if needed, important physical information in actual units, okay? When you put things on the computer, it's the same thing. Never put 10 to the minus 34 or 10 to the minus, okay? You have to use things of order 1, okay? And this is a good way of getting rid of all the H bars around, okay? We'll do this again for the hydrogen atom, similar technique, okay? There we will find that the relevant length is the Bohr radius, okay? And we will find an expression for it in exactly the same way we have found here, okay? The relevant energy is the Hartree energy, okay? And the system of units that you will write is the so-called atomic units that every experimentalist, okay, on Earth uses when discussing experiments on atoms, for instance. They will never give you numbers in MKS. They will tell you the energy is such and such Hartree, okay? This length is so many Bohr radius and things like this. Okay, good. So, by the way, this length is also called oscillator length for obvious reasons. Okay, this I wanted to tell you because it's not really so standard. I mean, it's nothing really difficult, but you very rarely find it stressed so much. Okay, so let me make things cleaner now, and let's proceed with the solution of this problem. Okay. Now, the solution could be just written in ordinary differential equations, and you have to write this is the second derivative, this is x squared, and in principle you try to solve directly the Schrödinger problem, or, which is an often used technique that works very well for this type of problem, to proceed in an algebraic way. Since I know you have seen it, okay, because this is, I think, part of the first course, okay, I will not spend too much time on that, but I want to just give you the main messages nevertheless again, okay? So, let us define two new operators. You see, it's x and p that you have there with commutator I. Let me define x plus ip, okay, over square root of 2. Let me call it A. This operator, you see, it's not Hermitian because x is Hermitian, p is Hermitian, but x plus I, another Hermitian operator, is not Hermitian, okay? Now, we have until now seen only Hermitian operators. So the question is, what is the so-called Hermitian conjugate of an operator? So we have seen that an Hermitian operator is such that if you have two states here, okay, then if the operator is Hermitian, it can travel there, and you have just A, psi 1, psi 2, okay? So if A is Hermitian. Now, if A is not Hermitian, you can define whatever is needed here to make the two things again to be the Hermitian conjugate, okay? So in general, you say psi 1, any operator psi 2 is equal to a Hermitian conjugate psi 1, psi 2. In other words, the Hermitian conjugate of an operator is whatever operator is needed to act on the left, okay, to get exactly the same scalar product as the operator when was acting on the right, okay? So this is the definition of a dagger, the Hermitian conjugate of A, okay? Obviously, if the operator is Hermitian, A dagger is equal to A. Now, you can prove in a very simple way that, so try to prove it, is an exercise for you. If you have two operators, both Hermitian, and you have A plus IB, then this operator is not Hermitian if A and B are, but the Hermitian conjugate is just A minus IB, okay? If A and B are Hermitian. If A equal to A and B equal to B, okay? So try to verify this. It's not difficult. It's the usual trick that when things act on the left, there is always the star, and you have to be careful. Okay. So therefore, this operator is not Hermitian, but I can define the Hermitian conjugate to be just X minus IP. Okay? And now it's very simple to verify the following thing. A commutator A dagger. How much it is? Well, it is 1 over square root for both, so 1/2. And then I have commutator of A plus X plus IP with X minus IP, okay? So X and X commute, P and P commute. The only two terms are this with this and this with that. If you keep track of both, you remember that there is an I in the commutator of X and P, and you verify that the two terms actually, because of the signs, are exactly identical. They cancel the factor 2. The I cancels the other I, and you get just 1, okay? So A and A dagger are two operators whose commutator is just 1. And this is very useful algebraically. We will see that we will often use we'll often interchange them, okay, by just using the commutator being equal to 1. Okay, now, they might seem very strange operators, but they're not so strange, okay? So remember, P is what? Is minus I, the derivative. H bar is put to 1, okay? So this operator here in real space representation is actually X plus the derivative with respect to X. Okay? Not so bizarre. And the other one is 1 square root of X, X minus the derivative with respect to X. Okay? They are innocent operators. Okay. Obviously, you can invert these two relationships. You can obtain X and P as a function of A and A dagger. Just sum or subtract the two, and you will immediately get that X is 1 over square root A plus A dagger, and P is 1 over square root of 2 times I, A minus A dagger. Okay? If you use this, you square and you sum, you can obtain the Hamiltonian. Okay? I'm sure that you have seen this algebra. Okay? Let's see, very quickly. 1/2 P square is the square of this. So you have what? You have 1/2 again. You have the square of I, which is a minus 1. And then you have the square of A minus A dagger. Okay, so I write it like this. This one is again 1/2 coming from the square root here. And then I have a plus a dagger squared. As you notice, I don't write the square directly. I could, obviously. I write it as product because in quantum mechanics, you have to remember that when you do the squares of binomial things, you have to remember the order of the objects, okay? So don't just use, for instance, here, a square plus a dagger square plus or minus 2a. You have to be careful. They are both in the opposite order. But the order is somehow, I mean, you can move them if you remember that a dagger minus a dagger a is equal to 1. Therefore, a dagger, for instance, is equal to 1 plus a dagger a. So you can always use that relationship to write one order in terms of the other, depending on which one is more convenient to you. Okay? Now, I want to be quick here, unless you tell me, no, please, we never understand this. So the quick thing I want to do is the following. There are essentially 2 times 2, 4, and 2 times 2, 4, 8 terms coming from these two things, okay? Some of them cancel. For instance, let's see. A and A, you see, has a minus 1/2 here and a plus 1/2 here. Similarly, a dagger and a dagger cancel. On the contrary, two of them, like a dagger and a dagger a, do not cancel. Actually, they sum exactly in the two things. For instance, let's look at a dagger a. You see here I have a plus 1/2 a dagger a from here, and here I have again plus 1/2 a dagger a. So total a dagger a. All right. Similarly, for the other term, that is a dagger, I have here plus 1/2 a dagger. And here I have another plus 1/2 a dagger. So this, okay? So the result is just 1/2 the sum of this. But now I can use the fact that a dagger is just a dagger a, and therefore the result can be written as 2 this plus 1, or a dagger a plus 1/2. Okay? I was a bit quick, but I'm sure you followed me and you have already seen this. Okay? So the nice thing about these two operators is that in terms of them, the Hamiltonian becomes of this form. Let me write it here. A dagger A plus 1/2. You might ask, 1/2 what? 1/2. The 1/2 times the identity, obviously, okay? So it doesn't do anything. Now, why is this simpler? Because you immediately see that if I find a state, for instance, such that, so let me call psi 0 a state such that a psi 0 is equal to 0. Okay? Then, obviously, the 1/2 gives me 1/2, but a acting on psi 0 gives me 0. Okay? So this object here, already I can conclude that is an eigenstate of the Hamiltonian, right? Eigenvalue, how much? 1/2. Okay? So I have found an eigenstate. You might say, okay, yes, but still I have to satisfy this. Okay? But you can always look at it. What does it mean? It means that I have to find the state psi of x such that 1 over square root of 2 x plus the derivative of x applied to psi of x is equal to 0. Now, the 1 over square root of 2 you can get rid of. And if you bring this on that side, you have that the derivative of psi 0 of x is equal to minus x psi 0 of x. This is much simpler a problem than solving the full hydrogen, Schrödinger equation. It's a very simple differential equation. What is the solution of this? you find the same function when you have an exponential, okay? But here you have the exponential times x. It means that you have to have a Gaussian, okay? So you can solve this by some constant times e to the minus x squared over 2. The 2 is needed so that when you take the derivative, you get just minus and not the 2, okay? This is an eigenstate, okay? The Gaussian is an eigenstate. C has to be found, obviously, by normalizing the Gaussian, which you know what to do. We did it in the first lecture, okay? So you can calculate this. You might ask me, how do I calculate the wave function, for instance, 3 angstrom away from the minimum of the potential? Well, this is x, okay? X is equal to x, big X over L. So this is also equal to e to the minus big X square over twice L square, okay? And L is h bar over m. So I can also write this in actual, sometimes you find it written this way in the books. You find it with all the h bars there, okay? You can do it, okay? Just substitute this there. And now you can put here x equal to such and such angstrom, calculate L, take the ratio, and whatever, all right? So you can reconstruct always whatever information you need, but you must admit that this way of writing is much simpler, okay? Everything has disappeared, it's just x squared over 2. All right. So I have actually solved this problem. And I have actually found a solution for the Hamiltonian. One, however, solution. In general, a problem like this admits an infinite number of states. Remember that the eigenstates of the Hamiltonian must be a basis for the Hilbert space. So one is not enough. You have to have an infinite number of them. Now, first of all, is this the ground state of the Hamiltonian? In other words, I found this to be an eigenstate, but it's not obvious it's the ground state in principle, right? The answer is yes, it is the ground state. And the proof is very, very simple. Let us calculate, suppose that I have an eigenstate, okay? Psi. Psi n, whatever. And let me calculate h tilde psi n. Okay? Generally, this is what is the eigenvalue En, if the state is normalized, obviously. Okay? But now, let us see. This Hamiltonian is just 1/2 plus A dagger A. Okay? So the 1/2 is trivial and is simply there, 1/2 plus psi n A dagger A psi n. Okay? Now, when you have an operator here, you can bring it on the other side. However, you have to put the dagger, the Hermitian conjugate. If the operator is Hermitian, no need, but this is not Hermitian. However, it's very simple to prove that A dagger is simply A, the usual thing, okay? So this object here is 1/2 plus A acting on psi n, A acting on psi n, okay? So with this, the scalar product of the state A psi n with itself. Huh? It is positive, exactly. Or 0, obviously. 0 if A annihilates psi, which is the case of psi 0, in fact. Okay? So the case where it is 0 is what we have done already. Okay? In general, it's positive. Okay? So this is the lowest one. All right? So this is a proof that this is the ground state. Now comes a kind of small algebraic machinery to calculate actually all the eigenstates.
I think this is true only in Hilbert space. Is that right? The inner product has to be... Okay, is it always true?
I always work in Hilbert spaces, never in other extragalactic spaces. So.
I know, but I saw they put a metric tensor when they calculate the inner
in quantum mechanics, non-relativistic quantum mechanics, you need no metric tensors whatsoever, okay? If you do try to quantize general relativity, I do not guarantee, okay? You probably need metric tensors here and there, but not here. Yes. Okay. Okay, is this clear? Okay, so let us construct now the other eigenstates. As an exercise, I'll do it for you practically, the first excited state, okay? So we did, maybe I should erase here some of the things. We found here in the energy axis, if this is 0, energy divided by h bar omega, by the way, okay? We found a value 1/2 here, okay? Now I'll show you that there is another one at 3/2, another one of 5/2, and so on, equidistant, okay? The difference between them is just 1 in units of h bar omega, obviously, okay? And we will classify them by an integer n, okay? So n was 0, 1, 2, 3, and so on, okay? So we just constructed the first, and now we will construct all the n greater than 0. Let me just do for you psi 1. The idea is very simple, and by the way, it's also used when you do second quantization for bosons, for instance. Okay, you introduce creation operators, okay, when you do second quantization, and this is exactly the form that those operators have. Okay, and in fact, even the commutation rules that you have, so a dagger equal to 1 is exactly the commutation rule between boson creation operator. Okay. In some way, this is telling you that the excitations of this harmonic oscillator behave a bit like bosons, okay? In fact, they are often called phonons in condensed matter, okay? They are just the quanta of vibrations that you can think of having in your system when you excite it, okay? In pretty much the same way, they mimic the quanta of the electromagnetic field that are called photons, okay? All right. Yeah. Second quantization you need when you have many indistinguishable identical particle-like fermions or bosons, okay? For instance, many helium-4 or many electrons, okay? There you need to account for the statistics of fermion or bosons. I will explain to you towards the end of the course very briefly what to do to deal with more than one particle, how to, what are the physics that wave functions have to respect, Pauli principle, for instance, for fermions, so anti-symmetries and things like this. And these are best captured if you work rather than with wave functions of x, y, z, x2, xy, I mean, for all particles, is best captured if you introduce those operators, okay? So you create particles directly with those operators in a way that the state is automatically correctly symmetrized or anti-symmetrized. But this later, okay? For the time being, I just anticipate that you will see similar things sometimes if you do second quantization. Okay, now the idea is pretty simple. A, as you have seen, distracts, okay, things, so annihilates this object that, by the way, is called the vacuum state. Vacuum state. On the contrary, A dagger does exactly the opposite. It creates, okay? So A dagger psi 0 is not 0, okay? And in fact, it's my candidate state. Let us verify that this is indeed a state that is also an eigenstate of the Hamiltonian, but this time, the first excited state. Let's see. Apply H, okay? So H tilde apply to A dagger psi 0. This is equal to, well, there is the usual 1/2 plus A dagger A applied to A dagger psi 0. Now, the 1/2, as usual, simple, no role, 1/2 there, times obviously the same state. Plus, now look at this, it's A dagger A dagger psi 0. Now, A really wants to go towards psi 0, because when it emits psi 0, kills it, okay? Now, the problem is that there is an A dagger in the middle, which is somehow protecting psi 0. However, you can always use those rules. Whenever you find A dagger in this way, you can substitute this with 1 plus A dagger A, okay? Now, the 1 then leaves what? Leaves 1/2 plus 1. You see that the other state is just A dagger A dagger psi 0, like that. Okay? So this one gives you the promised 3/2. And the other piece is actually with an A close to psi 0. So it gives you 0. Okay? So as you see, I have reconstructed an energy that is 1/2 plus 1 with the state that has a single A dagger in front. Okay? And this is the state. So if this was psi 0, this is psi 1 B equal to A dagger psi 0. Okay? It's a state with one excitation quantum, A dagger, created. Okay? You realize easily that you can play the trick again. A dagger squared, okay? So 2 times applied on psi 0. A dagger cubed applied on psi 0. They will also work, okay? And if you do the calculation, and I have given to you a number of exercises in the lecture notes, which are guiding you towards actually proving that these are all eigenstates with an increasing number of excitations, and the general, for a general n, you have that the energy is n plus 1/2 in units of h bar omega. Okay? By the way, I should talk to you a little bit about normalization. If psi 0 is normalized, you can verify that psi 1 is also normalized. Okay? This is very simple. You see, psi 1 would be, so psi 1 is just A dagger psi 0, okay, times psi 0 A, because when you bring it on the other side, you get this. All right? But A dagger is equal to 1 plus A dagger A. Okay? The 1 gives you 1, because psi 0 is normalized, and A dagger A, acting on psi 0, gives you 0 again. Okay? So this is also normalized. But when you go to higher states, so for instance, you construct this object, A dagger squared psi 0. Okay, you would be tempted to call it psi 2. Well, you can call it psi 2, but this psi 2 is not normalized. Okay? In principle, you have to put a factor in front, which happens to be essentially related to 1 over square root of factorial of 2 in this case. So in this case, it would be just 2, in order to normalize it. Okay? And in general, all the psi n that you could construct in this way, so A dagger n psi 0, okay, have to be appropriately normalized in order to be of norm 1. Okay? So in one exercise, I ask you to find, for instance, by iterative reasonings, a way of calculating this coefficient Cn. And you will see that there are factorials involved. Just because this switching thing, okay, which brings you 1, has to be repeated several times, and 1 easily become, okay? So there is, in fact, quite, I find, quite entertaining algebra that solves this problem. So let me just mention to you. So the solution in this case is that Cn is 1 over square root of n factorial. And by the way, I also ask you to look at this object that appears in the Hamiltonian. I erased it, this one. Okay? This object here is particularly nice. It's an operator that I call it n. I put a hat, okay, because it's an operator in general. But you can prove very easily that, for instance, if you act on psi 0, you get 0. If you act on psi 1, A dagger A applied to psi 1, okay, is just equal to psi 1. Okay? If you do A dagger A on psi 2, you get 2 psi 2. Okay? Because there are 2 A daggers. So A dagger A is actually counting how many A daggers there are to the right of it. Okay? So you can prove very easily that if you have a state with, say, n A dagger applied to psi 0, and you apply to it this operator A dagger A, then the operator simply restitutes to you a number that is n times the same state. Okay? You can prove this quite easily. It is, in fact, at the basis of showing that the Hamiltonian has eigenvalue n plus 1/2. Okay? The n is exactly, okay, what gives you this piece of the energy, because the other is the 1/2, this one. All right? So this operator is called number operator. Number operator. So please do it with some care. Okay? Here the normalization is irrelevant. You see, this state is not normalized. In this other exercise, I ask you to actually do the algebra to verify that the correct normalization is 1 over square root of n factorial. Okay. You can also deduce what happens if you take a state psi n that is correctly normalized. What happens if you create a further A dagger? Well, you would be tempted to say, well, you get psi n plus 1. Almost. Because they have this 1 over square root of n, each one of them, okay? And you verify very easily that you have here this factor, okay? Essentially because here you have A dagger to the n applied to psi 0 divided by square root of n factorial. You apply another A dagger, but this doesn't give you the correct square root of n plus 1 factorial that you should have here, but there is one less n plus 1, okay? So it's very simple to prove this. And in a similar way, you can prove that if you apply A to psi n, you destroy one of the excitations, so you go towards psi n minus 1, but there is a square root of n factor, okay? Now, both these things are very useful, in fact. When we will do perturbation theory, we'll do a few exercises where we perturb the harmonic oscillator with extra potentials, so much that the problem is no longer exactly solvable, but we can calculate perturbation correction to several quantities, and we'll have to calculate matrix elements of things. The best is to just use A and A dagger and to calculate the matrix element in this very simple way. Okay? One more notice on wave functions. If you open up a book, you will find that the wave functions of the harmonic oscillators are Gaussians multiplying by some polynomials that are called Hermite polynomials. Okay? Well, the ground state actually is the simplest polynomial, 1. Okay? So the ground state, let me draw it here. Is just our old friend the Gaussian. Okay? So the constant times e to the minus x squared over 2. Now, what about the first excited state? We have it here, in fact. Okay? So let me spend 2 minutes with you to calculate psi1. So this is telling us that psi1 of x is equal to the application of A dagger. If you remember, A dagger was x minus the derivative with respect to x applied to phi 0 of x, which we calculate to be c e to the minus, okay? So this is c over square root of 2 x minus the derivative of x times e to the minus x squared over 2. Let's calculate these simple things. X is simple. The derivative brings down minus x, right? But there is a minus, so it's plus x. So the result is c over square root of 2, 2x e to the minus x squared over 2. Okay? And the 2 just give me square root of 2. Okay? So you see that apart from this constant or normalization, it's x times e to the minus. Okay? So for 0, it is like that, and then it's something like this. Two things to notice. First, there is a 0 in the origin. Second, it's odd, okay? And eventually, obviously, it decays again like a Gaussian, essentially, because x makes very little contribution for large x. But it's slightly larger than the ground state, okay? Now, guess what? If I calculate psi 2, I have to have, again, the same A dagger applied to psi 1. Okay? Well, there are normalization, because remember, psi 2 has an extra 1 over square root of 2 factorial, 2. Okay? So this is psi 2 now. Psi 1 is this. Okay? So I can just write it now here. I substitute here c2 square root of 2, okay? And psi 1, I put an x here, okay? Is it clear? I'm writing now the same thing, because this is A dagger, applied to psi 1, which, however, has an x. Okay? So I have several possibilities. Well, x gives me x squared, okay? So this is square root of 2 times x squared e to the minus x squared over 2. When I take the derivative, I have two possibilities. The derivative acting on x or the derivative acting on the exponential. If I act on x, I get what? Minus 1. Okay? If I act on the exponential, I get a minus x coming down, multiplying this x is minus x squared, but there is a minus, so it's a plus x squared. Okay? So all in all, I have square root of 2c, 2x squared minus 1, e to the minus x squared over 2. Okay? And as you see, now I have a polynomial of degree 2. This is the second Hermite polynomial, by the way, often called h2 of x. Okay? So in, for instance, in 0 is now, if I have kept track of all factors in the same plot, it would be here something minus. But you see, this gets to 0 when x is equal to 1 over root 2. Okay, so there is actually a 0 now here, and then it does something like this, and then it's even, obviously. Okay, something like this. Okay, so this is psi 2. So you see now there are two zeros. This is a very general result. In one dimension, the successive eigenfunctions have no nodes for the ground state, usually, one node for the first excited states, two nodes for the second excited state, and so on with the increasing number of nodes. Okay? But since the potential is even, you have parity as a good quantum number. We will see this doing symmetries. The ground state is even, the first excited state is odd, the second excited state is even, third odd, fourth even, and so on, like the square well problem. Okay? Questions? Questions? No questions? If there are no questions, let us proceed a little bit. I want to at least start setting up the next problem we want to solve. Okay? Let's see if I have to mention something else. Oh, sometimes rather than finding psi n, you will find n. It means exactly the same thing. It's just a shortened notation. Also, instead of psi 0, you find 0. Okay? Often indicated in this way. It's the vacuum. Okay? It's not the 0 of the numbers. It's a particular state in the Hilbert space. Okay? Without excitation. But it's not 0. I mean, it's the Gaussian. Okay? So just to make, yeah. The question is, what do the nodes mean? Well, nodes are 0 of the wave functions, okay? First of all, just definition. A node of a wave function is a 0, a point where the wave function just touches the x-axis, okay? There is a quite general result is that the ground state has no nodes. The reason is that a node essentially costs energy, okay? If you have to go through a node, it means you have to oscillate. Oscillation means kinetic energy, okay? And usually it's better to avoid going through nodes, okay? You can in fact construct proofs that if I assume that the ground state wave function has a node, then I can construct a wave function that has no nodes that is in fact better in energy because it has less kinetic energy. So there are proofs based on this to show that there cannot be nodes in the ground state. And then there is also this result that I think is due to, mathematicians studying eigenvalue problems for Schrödinger-like operators, that the different eigenfunctions have an increasing number of nodes as you increase in energy. Huh? It is related to the, as the energy increases, the number of nodes increases, because mostly it's kinetic energy that increases, because the nodes cost kinetic energy. Obviously, there is a role also of potential energy, but it's mostly kinetic. But more than this, it's hard to say. I mean, you solve a problem, and you always find successive eigenfunctions that have an increasing number of nodes, and you learn that this is a theorem, in fact. Okay? But don't ask me to prove the theorem, because this is not the right diploma course. Okay. You can construct, for instance, psi 3, psi 4. By the way, you can, in fact, in principle, get the general recursive relationship for the Hermite polynomials. There is a little bit more of, you could probably sit for a while and think how to really solve this problem. You see that you always get this thing acting on the previous step, which generates a certain polynomial, and when this acts, you can probably sort out just an ingenious way of getting some recursive relationship. But I'm not asking it. If you have just a couple of hours to spend, you can probably sit down and try to see if you can find a way of getting them all in some nice way. Okay. Yeah.
We found negative energies.
Where? No. This is a negative wave function. The energies are there, are all positive. the ground state of the harmonic oscillator, I mean, the harmonic oscillator had, as I wrote it, this potential, okay, with the 0 in the origin, okay, 1/2 m omega square x square, or better yet, h bar omega over 2 x square. This, okay, so 0. Now, the energy cannot be smaller than the minimum of the potential, that is 0 now. And in fact, it is not only not smaller, but it's also positive. It's 1/2, because you have to pay a little bit. Okay, classical oscillators can sit exactly in the minimum without moving. Okay, so the minimum energy of a classical particle in this potential is 0. No kinetic energy sits there. Quantum mechanically, Heisenberg uncertainty prohibits that, because you cannot sit in a point with 0 velocity. If you sit close to a point, you should have some indetermination in P. And in fact, the best compromise between indeterminacy in X and P is exactly, you can try to show when, okay, if I have some delta X square, this costs an energy that is this, okay? If I have the same delta X square, this costs a kinetic energy that is this, okay? What is the best I can do? Paying the same price, okay? So really doing this, okay? What is delta X? L, okay? So L is also the essential, the width of the best compromise between paying kinetic energy and paying potential energy, and the result is obviously, as you know, h bar omega over 2. Anything that disfavors, for instance, kinetic energy in favor of potential energy, or vice versa, pays more. Okay, this is the best you can do. You can prove it. In fact, I mean, well, you can write some. Never mind. Okay, is it clear? Okay, so you cannot sit right at the minimum. There is an uncertainty which is exactly L square, and therefore you see a little bit of the surrounding of the minimum, and this costs a certain energy. It is absolutely stable, one of the best. No. This depends on your prejudice on what it means to be stable. Stable is not sitting on a chair. Okay? Stable means that the thing is there. Okay? It fluctuates around the minimum. These are called quantum fluctuations, by the way. Okay? If you hear about quantum fluctuations, those are the quantum fluctuations. There are no thermal fluctuations. Okay? The system is at 0 temperature. Okay? But still, the energy is not 0. There are quantum fluctuations, and the particle kind of feels the surrounding. It is stable. This. If it was not for the kinetic energy, then you would just minimize the energy by sitting in 0. But if you make a wave function that is strongly peaked in the minimum, you pay a lot of second derivative and a lot of kinetic energy, and this costs too much. Okay?
So the concept stable in classical mechanics is different?
Yes, because classical mechanics is different from quantum mechanics.
Yes.
Yeah, but not this. This is a perfectly stable system. I mean, the energy cannot decrease in, I mean, instabilities usually have to do with things that go away. This is a very nice and stable situation. Nothing really so bad. It's just, there is no an equilibrium with the static value of X and P, because quantum mechanics forbids that. It's Heisenberg. It's not me, okay? So I'm sorry for that. All right. Let me just at least start setting up the hydrogen problem, okay, which is the next. Well, we have really a few minutes left, so maybe I'll just write the the Hamiltonian and tell you what we are going to do in the next couple of lectures, in fact. It takes a little bit more for the hydrogen atom. Now, the Hamiltonian, in principle, describes a nucleus of a certain charge, not necessarily plus E, it could be plus ZE, okay, at a certain position, and an electron, so a negative charge that somehow orbits around, okay, it's attracted by it, okay. So if I call, for instance, 1 and 2, the position of momenta of these objects, the Hamiltonian would be P1 square over twice the mass of 1 plus P2 square over twice the mass of the second, minus the charge, in general is Z, I put it there, R1 minus R2, Coulomb potential attraction, okay? And these are momenta, three-dimensional momenta of the two particles, the electron and the proton. They are distinguishable, obviously. They are not identical objects, okay? But first of all, this is already a substantially, in principle, complicated problem because you have two three-dimensional coordinates. So it lives in a six-dimensional space, this problem, okay? So the wave function would be a six-dimensional space function. Well, as a first thing, we will, this is very similar to what you do in classical mechanics. We will separate the problem into a center of mass problem and the relative motion. Remember that to solve the Kepler problem, the problem of, say, Sun and Earth, the two-body problem, you can do it because you can separate center of mass from the relative motion. The center of mass has, in fact, a very simple Hamiltonian. Is P square over twice the total mass. Nothing, no potential, because the center of mass is free to move, obviously, okay? So I'm writing the Hamiltonian really into the center of mass part next time we do it, okay? Plus relative momentum divided by twice the reduced mass. Remember, in the classical two-body problem, you introduce a total mass and a reduced mass in this way. Exactly in the same way you do here. And I don't write for you the expression for the momenta because there is a little trick in the relative momentum. We'll do it next time. Minus Z E squared over R. R is now simply the relative coordinate. This, going from, say that you have R1 and R2 is R1 minus R2, the relative coordinate, okay? Now, these two things don't talk to each other. This commutes with this, okay? So it's once again a problem where the Hamiltonian is written as sum of two commuting pieces, center of mass and relative motion. So this is very simple, a free particle, nothing really plane waves type of things. The relative motion is what will interest us, okay? But it's now three-dimensional, okay? So from six-dimensional, we have reduced already to three-dimensional, which is much better. Next, you notice that this potential depends not on the angle, but just on the distance between the two particles, okay? It's one of the so-called central potentials, okay? More in general, you could have a potential like this, depending only, again, on the distance, not on the angle, okay? So much of the discussion we will do preliminarily on this problem applies to any central potential. And essentially allows you to separate the problem, the 3D problem, into a 1D radial problem plus a 2D angular part. In fact, the angular part all appears here. So it all appears in the Laplacian part. Okay? Not here. Here there are no angles. So you could already guess what will be the angular part if you open your book on classical electromagnetism. You have done probably many problems, okay, in which you will see the Laplacian in 3 dimensions. Laplacian in 3 dimensions has a piece involving derivative with respect to theta and phi, the angles, okay? And as you know, there are special functions that appear in those problems, okay, which are the spherical harmonics. So this problem will be solved by introducing the spherical harmonics of theta and phi, okay? Classified by two indices. I will do this in some detail because these have a very important physical meanings. They are eigenfunctions of angular momentum, okay? So we will introduce for the first time a very important new operator that is not x or p, is the angular momentum, so it is r vector p, okay? So we will introduce this, study its property, and really understand that the eigenfunction of angular momentum can be written in terms of those special functions appearing in the book cover of Jackson or whatever and involved in the Laplacian, okay? Once we understand this, the radial problem becomes really a one-dimensional problem, okay, which will have a reasonable, simple look, okay? And we will, at this point, explicitly use the fact that this is 1 over r and solve it, okay? But much of the process to arrive to this problem here is pretty general for a central potential, okay? The final part, solutions of the 1D radial problem, is specific of hydrogen. And this is an exact solution that we will discuss, okay? Is this clear? So this is the plan of the next 2 lectures. Okay.